Welcome. In this video lecture, we will discuss demodulation of exponential modulated signals where information is represented over instantaneous phase or instantaneous frequency of the carrier signal. To detect information from such modulated signals, we need a system which has a selective response in terms of phase or frequency for the input signal. There exist several such systems, so let's start the discussion with a direct differentiator. Since the information signal cannot be passed through a wireless channel in its original form, therefore we require modulation of the information signal over a carrier signal which has properties suitable for transmission and suitable for propagation through the wireless channel. In our previous lectures, we referred the information signal with m of t and the carrier signal with f of t. An information signal is a baseband signal which is composed of low frequency components that occupies the band from 0 to B Hz frequencies, while a carrier signal is a pure sinusoid that is of a frequency from the passband where transmission is suitable in all aspects. That is, the carrier signal defined as a pure sinusoid signal. Information can be represented over this carrier signal in terms of its peak amplitudes that we studied, or in terms of introducing the changes with respect to information signal in the instantaneous phase or frequency of the carrier signal. For such modulation schemes where information is represented over instantaneous phase of the carrier signal are referred as angle modulation schemes, while if the phase is directly changed with respect to the amplitude of information signal, such modulation scheme was referred as phase modulation. And if the instantaneous frequency of the carrier is modified with respect to the amplitude of information signal, we referred such signals as frequency modulated signals. While in frequency modulated signals, we are aware that phases are changed with respect to the integral of information signal, and in phase modulated signal, the instantaneous frequency of the carrier signal is modified with respect to the derivative of information signal. In generalized form, we represented the exponential or angle modulated signals as where psi of t can take the value as information signal itself to represent phase modulated signals, or the integral of information signal to represent the case of frequency modulation. To demodulate such signals at the receiver side in order to obtain the information signal from the received signal, we require a demodulator which can extract information from the phase or frequency of the received modulated signal. For the remaining part of this lecture, we will conduct the demodulation of only frequency modulated signals, where this analysis can be extended to understand the demodulation of phase modulated signals. So if we have a frequency modulated signal received at the receiver, then the demodulator's design is required to detect information from the instantaneous frequency of the received modulated signal. Therefore, for the demodulation, a system is required which can discriminate among different frequencies of the received signal and translate the fluctuations in the frequencies in order to detect the information signal. The information in such frequency modulated signals resides in the instantaneous frequency. Therefore, a frequency selective system with a transfer function which can discriminate among different frequencies over the band of a frequency modulated signal can help in obtaining the output proportional to the instantaneous frequency, as the changes in instantaneous frequency represent the information signal. Therefore, detecting the instantaneous frequency translates into the detection of information signal. A representation of such systems can be through the direct differentiation of the received signal, that is passing the received signal through a derivator. So as first step of the demodulation, if we pass the received signal through a derivator, that is if we take derivative of the received signal with respect to time, we can express it as As we know that derivative of sine of theta of t, for example, with respect to time is equal to cos of theta of t multiplied by the derivative of theta of t, while any constant peak amplitude along sine of theta of t will be treated as a constant and it remains as the same scaling factor in the derivative signal as well. So if we accordingly apply the derivative operator in equation number 1 here, we can express the signal as AC into the derivative of instantaneous phase of the sinusoid multiplied by cos of the instantaneous phase. As there are two terms being added inside the derivative operator here, we can calculate its derivative as independently for both the terms and add up the result of the derivative operator for both the terms, while the derivative of the integral of information signal is information signal itself in its original form. So after taking the derivative of the frequency modulated signal which was received at the receiver, we obtain a signal which has representation of information signal on its phases and frequencies, as well as information signal here is influencing the peak amplitudes of this signal. So we have information signals representation both in phases and in amplitudes of this signal. If we analyze the part which represents the peak amplitude of this signal, we have information signal being scaled by a constant number and then being shifted by a constant number along the vertical axis, and further another scaling factor is scaling the signal, while there is only one signal which has variations with respect to time, that is information signal in its original form. All the other factors in the peak amplitude of this signal are constant numbers which only cause either scaling or shifting along the vertical axis, that is along the amplitude axis. So we can express that this peak amplitude is directly proportional to the information signal, which was the case for double sideband amplitude modulated signal, where information was represented on the peak amplitude of a certain sinusoid of passband frequency. So it is an amplitude modulated signal and a frequency modulated signal at the same time. So if we plot the received frequency modulated signal which was being fed as input to the derivator, and also plot the output of this derivative signal, that is equation number 1 and equation number 2, as input and output of the derivative operator respectively, we received a signal which had a constant peak amplitude across all the time intervals, that was plus AC and minus AC, while its frequencies are being modified with respect to the amplitude of information signal. Any variations observed in the amplitude of information signal were directly translated in the frequency fluctuations of the carrier signal at the transmitter side. So the frequencies of this signal represent the information signal's amplitude. For the intervals we have a high frequency here, it represents a high amplitude of the information signal, while for the intervals where a low frequency defines this frequency modulated signal represents a low amplitude of information signal. After this signal was passed through a derivator, we have observed from equation number 2 that the derivator translates all the frequency variations in the received signal into the amplitude variations as output of the derivator. So at output of this derivator, we have a signal which represents the information signal over its instantaneous frequency as well as peak amplitude, that is jointly modulated in terms of frequencies and amplitudes. So for the intervals, there was a low frequency observed. After taking derivative, we will have a low peak amplitude of this derivated signal. As evident in this equation, that peak amplitudes are directly proportional to the information signal, as well as the phases are being modified with respect to the integral of information signal. So information being directly added in the frequencies here and information being directly added in the peak amplitude here is directly influencing both the frequency and amplitude of this signal. For the time spans, we have a low amplitude. We also have a low frequency, that is number of cycles per second experienced by this signal. And for the time spans, we have high frequency. We also have a high peak amplitude of the modulated signal, as the frequency and amplitude are directly being modified with respect to the amplitude of information signal. That is, the envelope of this signal represents the information signal in its original form, which is equal to information signal if we ignore the scaling and shifting parameters that are constant numbers here. So if we pass this joint frequency and amplitude modulated signal from an envelope detector, we can detect its envelopes, which are a direct representation of the information signal. As the information is clearly being represented on the amplitude of this signal, we can apply an amplitude demodulator to obtain the information signal from this signal. So together, the block diagram of the demodulator, which has two blocks, can be illustrated as a frequency modulated signal being applied as input to this system. After taking its derivative, we obtained a signal which is both frequency modulated as well as amplitude modulated. Therefore, an envelope detector can be applied here to detect the envelopes of this joint frequency and amplitude modulated signal, where precisely the envelopes are equal to, that is, information signal being scaled and shifted along the amplitudes. So both the scaling and shifting parameters being constant and not being a function of time, we can express that the output is a direct representation of information signal. This type of demodulator is also referred as a slope detector because it detects the slope of input frequency modulated signals. While in this type of demodulator, in this form, has some problems, some challenges which can practically be encountered. For example, we have considered an ideal frequency modulated signal here. An ideal case, a constant peak amplitude across all the time intervals of this signal. That is, along time, we have considered a fixed peak amplitude where frequencies of this signal are varying with respect to time, and any change in frequency is representing the information signal, where the peak amplitude of this signal is constant throughout all the time instances. That is, a constant value AC along both positive and negative vertical axis, whereas practically various reasons can cause some variations in the peak amplitude of this frequency modulated signal. For example, some noise signal can cause changes in the peak amplitude of this signal. So practically we may experience some fluctuation in the peak amplitude of this signal, and it may not be an ideal case where the peak amplitude of the frequency and phase modulated signals are a constant number. So for this case, if the peak amplitude is not a constant number, that is, we have received a frequency modulated signal at receiver, while the peak amplitudes of the information signal are also a function of time. While ideally this peak amplitude should be a constant number, that is AC, where practically we may experience this peak amplitude as time varying, imposed by different noises or any other distortions experienced in the hardware or during the propagation through wireless channel. If such a signal is passed through the derivator, the expression has two parts which are function of time. Therefore, the derivation by parts will be applied to obtain the derivative of this signal. That is, the first part in its original form multiplied by the derivative of second part. That is, while the received frequency modulated signal can be a cos wave or a sine wave, as in the initial part of this lecture we have considered a sine signal here. So in order to make it uniform, if we consider a sine wave here, then its derivative will be a cos. So further, the second part will be the derivative of the first part, that is a of t, and if the derivative of a of t is a dot of t multiplied by the second part in its original form. So for this problem that the peak amplitudes of frequency modulated signals received at the receiver are not constant along time, while there are some variations introduced by the noises and by some distortions imposed by wireless channel. At the output of this derivator, ideally a joint frequency and amplitude modulated signal was expected to be derived, whereas in this practical case, at the output of this derivator we have received this signal which has two parts being added. The first part has information signal being represented in the instantaneous frequencies as well as information signal being represented on the peak amplitudes of this signal. While in the peak amplitudes part, this parameter is no more a constant number while it is a time varying number, which is the time varying peak amplitude of the received signal. Additionally, we have another part being added, which is the derivative of information signal being represented at the peak amplitudes of a sine wave, and the sine wave has information signal directly represented over the instantaneous frequency. So the composite signal, after adding these two parts, will not have the information signal being directly represented over its envelope. So after applying envelope detector, we may get envelopes jointly for both of these signals, and the output received after detecting its envelopes will be proportional to information signal, and the derivative of the time varying noise added in the peak amplitudes of received frequency modulated signal. So ideally this part should have been a constant number while this part may not have been received. To solve this problem, as the problem is clearly the variations received in the peak amplitudes, that instead of AC being a constant number, we have received a time varying number. So the solution lies in forcing the peak amplitude of this received signal to be a constant number instead of it being a time varying number. So we need some additional blocks here to perform this task, while if a time varying sine wave is received as input, and after passing it through this block, we intend to convert its peak amplitudes to be constant instead of time varying without interrupting any variations received in the phases of this signal, as information is being represented in the phases either directly or indirectly. So without changing the instantaneous phase of this received signal, by keeping it same, we only intend to force the peak amplitudes from time varying to constant peak amplitudes. And we need to think of a system which can help us to perform this task. These observed variations in the peak amplitude of angle modulated signal can be eliminated by a system which is referred as band pass limiter in the literature, that has two blocks, a hard limiter followed by a band pass filter. A hard limiter is defined as by this function. For example, if we feed a certain signal x of t as input to the hard limiter, and for the time instances we have the amplitude of x of t greater than or equal to 0, we force the output of the hard limiter as +1, and for the time instances where the amplitude of the input signal is less than 0, we force the output of hard limiter as -1, and we obtain a certain signal that is y of t. This system represents a limiting operation, and the output signal is limited to two predefined fixed amplitude levels, that is +1 and -1 in this case. So for any amplitude greater than 0 will be mapped at +1 amplitude, and for any amplitudes being less than 0 are mapped at -1. So if we plot some example input signal here, if we take a time varying frequency modulated signal being fed as input to this system, it is defined as the frequency variations in this signal represent the information signal itself, while any variations in the peak amplitude of this signal is the problem which we want to eliminate. That is, we want to force the peak amplitude of this signal to a certain constant number while keeping intact the variations in instantaneous phase of this signal. After passing this signal through a hard limiter will force this signal's amplitude to two fixed predefined amplitude levels, that is for this case +1 and -1. For the cases where the amplitude of this signal is higher than 0, for example from time instant 0 to a certain time instant t1, for this case we have an amplitude greater than 0. So After passing this signal through a hard limiter, we will obtain an amplitude equal to +1 for this time span. Similarly, for the time span where the amplitude is less than 1, the output signal generated from this hard limiter will have a constant amplitude that is -1, and so on. It can be observed that the hard limiter's output is a square wave of unit amplitude regardless of the incoming sinusoide's amplitude. We know that square waves can be expanded through Fourier series expansion. For example, for the case that if cos of theta was input to the hard limiter, for the span where its value was greater than 0, we have limit its output amplitude as +1, and for the time spans where its amplitude is less than 0, we have limit its output amplitude as -1. We can further thoroughly define it as for the time instances where the cos of theta had a 0 amplitude, the output signal is also forced to have the same 0 amplitude. The output signal that we have referred as y of t. The square wave can be expanded by employing Fourier series expansion, and it can be represented as a sum of multiple sinusoids, that is, and so on. Particularly for our case, theta is a function of time which is defined as the running phase plus a shift in phase caused by the integral of information signal, which represents the case of frequency modulated signals. So if we substitute the value of theta in equation number 3 here, we can represent the case if a time varying peak amplitude variant of the frequency modulated signal is received at the input and fed as input to the hard limiter on the receiver, the output signal will be represented by this equation number 3. So the first part of this expression has theta in the phases, so we'll generate a certain frequency band where omega c will be its central frequency, and the second part of this expression will cause deviation in its frequencies, while the peak deviation we have represented with delta f was proportional to both the constant scaling factor kf, the peak amplitude of information signal. The second part has 3 being multiplied with the theta, so we will have its central frequency as 3 times the central frequency of the first part, and the deviation which is being caused by the second part will also be multiplied by 3, and the deviation or the peak frequency deviation experienced in this second part will also be 3 times higher than the peak frequency deviation experienced in the first part, and so on. This third term has 5 as its scaling factor of phases, so we will have the central frequency as 5 times omega c, that is 5 times higher than the central frequency of the first part, and its band will also be 5 times expanded, 5 times higher bandwidth compared to the bandwidth of the first part. So we can conclude that the frequency of the first part, being omega c, is sufficiently different from the central frequency of the second part, that is 3 times of omega c. Omega c or fc is a passband frequency, that is a high frequency from passband. For example, if we take it as 1 gigahertz, then this second term will be centered at 3 gigahertz frequency. That is, both first and second terms are 2 gigahertz apart from each other. Therefore, by using a band pass filter, a cheap band pass filter, we can easily stop all the other bands and pass only the first term of this expression. That is, if y of t is fed as input to a certain band pass filter that is tuned at frequency of omega c and passes a band equal to the bandwidth of frequency modulated signals, then the output of this signal will be observed as, where for the case of frequency modulated signals, this theta of t is equal to, we can see that after performing these two operations, passing the received signal that had time varying peak amplitudes from a hard limiter followed by this band pass filter, we have converted its peak amplitudes into a constant number, that is 4 by pi. So by adding these two blocks as the first blocks of the receiver side, we can eliminate any variations received in the peak amplitudes of the received frequency modulated signals. So at the receiver, a signal with time varying peak amplitudes was received instead of its peak amplitudes being a constant number ideally. After passing this signal through a hard limiter, the hard limiter converted this input sinusoid into a square wave by retaining the information of frequencies. While forcing its amplitudes to +1 or -1, we received. Then as second step, we can pass this signal from a band pass filter which pass the first part of this expression and stops all the other high frequency components which are sufficiently apart. For example, this omega c is sufficiently different from 3 times of omega c, so a cheap filter can easily stop all the high frequency components of this expression. We have a signal which has constant peak amplitudes after processing it through these two blocks. Then we can pass the signal through the derivator, which we have discussed earlier, will translate the variations of its frequencies over its peak amplitudes. After passing it through the derivator, we will obtain a signal which will have some representation of information signal on the peak amplitudes as well as on its frequencies. If this is a frequency modulated signal, then psi of t represents the integral of information signal, while the derivative of information signal will be the information signal itself in its original form. As the information will be translated from the phases to the amplitudes, we can use an envelope detector as last block here to detect its envelopes, which will produce 4 by pi into the derivative of psi of t. If psi of t is the integral variant of information signal, we will receive as output of this block proportional to the information signal. While precisely for the case of frequency modulated signal, we will receive, that is the output, approximately equal to information signal. The derivator in this block diagram can be realized through different realizations. For example, as the derivator computes the slope, where the equation to compute slope of a certain signal, for example, amplitude of that signal at time instant t1 minus the amplitude of that signal at some previous time instant, let's say t0, and divided by the difference between these two time intervals, that is t1 minus t0. So if the difference between these two time instances is equal to delta of t, y of t is being fed here, and we introduce a delay here, a delay equal to delta t, then if at the first branch before the delay there is the sample of this signal y of t1 at time instant t1, then after this delay we will have some previous sample of this signal. If the delay is equal to delta t, then we will have the sample y of t0 as output of this delay. Then after performing simple addition, we will obtain at this branch the numerator of the slopes equation. Then if we scale this variance of the signal by a parameter equal to 1 divided by delta t, then we can obtain the derivative of this signal y of t. If y of t is the input signal, we will get the derivative of y of t as output of this system. And this block diagram can be used to realize the derivative operation being used in the demodulation of angle modulated signals here. So an appropriate choice of delta t can help to obtain a realistic derivative of the input signal. Ideally, we want delta t to be infinitely small. This derivator block here translates the frequency variations of the input signal over the peak amplitude variations of the output signal. So the derivator can also be realized by observing its response in frequency domain as a frequency domain filter or a system which has a frequency selective response. So for example, if the signal being fed as input to this system has constant peak amplitudes while the frequency variations represent the information signal, that is a normalized frequency modulated signal in time domain. After passing it from this derivator, we have observed that all the frequency variations will be translated on the amplitudes. So the response of derivator in frequency domain can be represented with a straight line, for example, from the bands fc minus delta f up to fc plus delta f. If this h of omega, a straight line response, represents the derivative operation here. So if we plot the input frequency modulated signal in frequency domain here, if you recall, a sink positioned at fc frequency was generated, while for different amplitudes of the information signal, this sink experiences a shift along the frequency axis when a maximum amplitude of the information signal is observed, that is a peak amplitude of information signal. A maximum shift in the central frequency of this sink is observed, and a maximum deviation, that is delta f, is experienced in the frequency of the modulated signals. And similarly, when a negative peak of the information signal was observed, the sink was shifted to maximum deviated along the negative side positioned at fc minus delta f. That is, for some information signal, any changes in the amplitudes of information signal are directly reflected on the instantaneous frequency of the frequency modulated signal. If the information signal's amplitude is observed as 0, a sinusoid equal to a sample interval, the Nyquist sample interval, was generated, and the Fourier transform of a sinusoid for a limited duration is a sinc function. So for the time interval when the amplitude of information signal is experienced as equal to 0, then the modulated signal will have a frequency exactly equal to the carrier frequency, while along an increase in the amplitude of information signal, a shift in this sinc will be experienced when a positive peak amplitude of the information signal is observed. We experience a maximum deviation in the frequency that was referred as delta f, and we experience the sinc positioned at fc plus delta f. Similarly, along a decrease in the amplitude of information signal, a decrease in the frequency of modulated signal will be observed, and for the time instant when a negative peak, for example minus mp, is observed, the frequency of the frequency modulated signal will be fc minus delta f, and sinc will be positioned at fc minus delta f. That is, 0 amplitude representing sinc positioned at fc frequency, positive peak amplitude representing the sinc positioned at maximum deviated towards the right side, and negative peak amplitude representing the position of sinc as deviated maximum away from the carrier frequency towards the left side. So this amplitude axis is being directly mapped on this frequency axis. So for a particular time instant of the information signal, we will just observe one sinc in the frequency domain, and the position of that sinc function will represent the amplitude of information signal. Therefore, the deviation from carrier frequency towards the right side represents the shift in the amplitude of information signal from 0 to the positive peak, while a shift from the carrier frequency towards the negative side represent the change in the amplitude of information signal from a 0 amplitude to the negative peak amplitude. Therefore, if we pass this frequency modulated signal through a filter h of f, as a result, we will experience scaling of these sinc functions with respect to the response of this filter in frequency domain. As we have modeled the response of this filter with a straight line with a low magnitude for lower frequencies and a higher magnitude for higher frequencies, After multiplication of these two signals, we experience scaling of the sink with respect to its position in frequency domain. When sink is positioned at a higher frequency, for example at Fc plus delta F, the filter will cause an increase in the power of this signal as the filter has a higher magnitude for this frequency. While when the sink is positioned at a low frequency, for example at Fc minus delta F, the response of filter being a low magnitude for this frequency will cause a decrease in the amplitude in the power of the modulated signal. So while along the changes along the fluctuations in the position of this sink which represents the information signal, we will experience a directly proportional change in the amplitude of this output signal of the filter, which represents exactly the derivative operation. If a frequency modulated signal where frequencies were being fluctuated with respect to the information signal along time was fed as input to this filter, which has a Fourier transform as equivalent to this signal. After passing it through this filter, frequency dependent magnitude scaling is caused here, directly proportional to the frequency of the signal. Variations in its peak amplitudes are being caused. So Fourier transform of this signal can be represented as by this signal. So this is the exact operation which the derivative operator was performing. The derivator was translating the frequency fluctuations over the amplitude fluctuations of the derivator's output signal, which is exactly the operation which a filter with this response is providing. This method is also referred as slope detection method. This design suffers from the fact that the slope of this filter h of omega or h of f is linear, is a straight line over only a very small frequency span. Hence, designing such filter which has a straight line response over a very small frequency band can cause considerable distortions in the output signal. Therefore, practically, such a response is usually modeled by using two Gaussian filters, which leads us to the design of a balanced discriminator, which is a popular frequency demodulator. That is response of this filter being a straight line, linearly increasing line for the frequency span Fc minus delta F up to Fc plus delta F with its central frequency being Fc can be modeled with two parallel Gaussian filters. For example, if a Gaussian filter of response as bell shape positioned at Fc plus delta F and another Gaussian filter centered at frequency Fc minus delta F, while an inverted Gaussian filter can together, if applied in parallel, provide a response for this band approximately as a straight line. That is, if we add these two Gaussian filters, then for the band from Fc minus delta F to the band Fc plus delta F, the tails being overlapping for these two Gaussian filters, we get a response equivalent to the response, the ideal response of a derivator that was a straight line between this band, while we are not concerned for the response for the bands other than this particular band. So the response of a straight line that was a realization of the derivative operation can be approximately modeled with two parallel filters that are cheap filters, that are easier to design filters, that are bell-shaped filters. So if we use this realization by applying two parallel Gaussian filters, such a demodulator is referred as a balanced discriminator in the literature. That is, if the input frequency modulated signal, after removing its amplitude fluctuations, amplitude variations, is being fed as input to the system, to the demodulator, that was AC cos of omega ct plus psi of t. So instead of using a derivator, if we apply these two Gaussian filters in parallel on two different branches, one being centered at Fc plus delta F and other an inverted Gaussian filter being centered at Fc minus delta F, while choosing an appropriate bandwidth of these filters such that the tails appropriately overlap with each other to cause a straight line response for the band between Fc minus delta f up to the frequency Fc plus delta f. And after performing the derivation, if we pass these two parallel branches signals from the envelope detectors, we can obtain information signal as output. That is, this part with two parallel branches is performing the operation that the derivator was performing, and this branch has two parallel envelope detectors are detecting information from the envelopes, which was the envelope detector block. That was the second block in the demodulator we have studied in this lecture. If a frequency modulated signal is provided as input to this direct differentiator, then the frequency variations are translated over the amplitude variations, and amplitude variations can be detected with an envelope detector, and information is demodulated at the output. A frequency discriminator, a system which discriminates between different frequencies and provides scaling in different way to different frequencies, that is discriminating different frequencies by providing different magnitude scaling to different input signals frequencies, and with two balanced branches. That is why it is referred as a balanced discriminator. So at the receiver, if a frequency modulated signal is received, since due to any noise introduced by the transmitter or receiver's hardware or any distortions imposed by the wireless propagation channel, we may experience a time varying amplitude of this frequency modulated signal. Therefore, to eliminate the time variations from the amplitudes of this frequency modulated signal, we employed these first two blocks, odd limiter and a band pass filter. Then by performing the derivative of this frequency modulated signal, which has constant peak amplitudes, translates the variations from the instantaneous frequency of the frequency modulated signal over the peak amplitudes of the frequency modulated signal. So as a response, we received a signal here which was both amplitude modulated and frequency modulated. So after translating the variations from instantaneous frequency and phase of the modulated signal over the amplitudes, we employed an envelope detector to detect the envelopes. That is, over the envelopes, it was information signal being represented. Moreover, we have also seen that this derivation operation can be realized through different methods, where employing two parallel Gaussian filters to achieve the response equivalent to the operation of the derivation is a popular type of this class of demodulators, which is referred as a balanced discriminator. So this is the slope detection method to demodulate the information from the received frequency or phase modulated signals. If instead of a frequency modulated signal, a phase modulated signal is provided as input to this system, where the phases are directly influenced with respect to the amplitude of information signal, then as the derivation operation is being performed over the envelopes of this signal, instead of information signal, we will have a derivative of information signal. After detecting the envelopes, that will be the derivative of information signal, we will need an additional block to integrate it and obtain the information signal in its original form. So for the case of demodulation of phase modulated signals, we need this additional block here. Other than this design, we have several other designs for demodulation of such frequency modulated signals. For example, a zero crossing counter, a digital circuit which counts the zero crossings of the frequency and phase modulated signals. While counting zero crossings, we can estimate the instantaneous frequency, and instantaneous frequency has a direct or indirect representation of information signal over it for the case of frequency and phase modulated signals. Furthermore, phase lock loop, which we studied in chapter number 4 to synchronize the phases of two signals, can be directly used in its original form as a demodulator of such angle modulated signals. As a phase lock loop tracks the phases of the input signal, that is exactly precisely the operation required here for the case of frequency and phase modulated signals being fed as input to demodulate the information signal. So we will study this design, a phase lock loop based demodulator, in our following lecture. Thank you for attending this lecture. I hope you gained a reasonable understanding of the topic. If you have any question or comment, you can write me through email or we can discuss it during our upcoming online session.